Hello everyone, this is Ahmedabbasi from EEE 236 class. I'll be discussing with you guys regarding the flexible transistors. I'll be going through how flexible transistors work, what are the basic difference between the conventional and the flexible transistors, and throughout this presentation you will know some key concepts and some key aspects of flexible transistors. And let's kick off and start with the flexible transistors. So here's the outline for the contents which we'll be covering throughout this presentation. Initially we'll be introducing flexible transistors. We'll get an introduction of flexible transistors initially. After that we'll have a look at what are basically flexible transistors and what is the background of research on flexible transistors. After that we'll see the fabrication steps, how flexible transistors are fabricated, what are the basic building blocks and key concepts involved in the fabrication of flexible transistors. After that we'll see the performance enhancement of organic field effect transistors. Basically, how can we enhance the performance of overall flexible transistors, what can we do, what are the techniques applied for the performance enhancement. After that we'll see some key applications and implementations of flexible transistors in modern world, and then we'll conclude our presentation. As you would know from the title, this slide basically introduces the flexible transistors, and as you would know that this presentation gives us the basic idea of about flexible transistors, the step involved in the composition of a flexible transistor, not only the formation but its application and implementation in real case scenarios. Flexible electronics is one of the most ardently followed aspects of modern day electronics by the researchers, and this paper would also prove out to be very helpful and informative for the beginners who want to have a basic know-how of flexible transistors. So let's study how flexible transistors are made, what are the fabrication steps, how can we enhance the performance of flexible transistors, and after that we'll have a look at the application. So let's start with it. Conventionally, we know that a transistor is a rigid structure composed of a substrate and an oxide layer and three terminals. But as far as a flexible transistor is concerned, it is one which does not have a rigid structure. It is basically made of thin film organic transistors, or you can say organic field effect transistors, which are made of carbon-based materials such as graphene, carbon nanotubes. These carbon-based materials are the basic building blocks for the flexible transistor, and these provide this flexibility to the conventional type of transistor. Basically, what a flexible transistor offer is that, as the name suggests, it could be successfully used in packages that can be curled up, wrapped, or bent. This will enable us to have a display screen that could be bent, rolled up, basically, or you can imagine a computer screen that could be rolled up and carried in your pocket. So basically, this type of phenomena are possible by using flexible transistors. The background of research on flexible transistors ultimately leads us to the history of flexible electronics. 40 years ago, single crystalline solar cells were thinned to raise power to weight ratio for use in extraterrestrial satellites. Because these cells were thin, they could be wrapped. Today, silicon integrated circuits are being thinned so that they also become flexible. Flexible can mean bendable, non-breakable, lightweight, etc., etc., and these properties make it much more interesting and accessible. Flexible electronics promise an entirely new design tool, like for instance tiny smartphones that could wrap around our wrists, or flexible displays that could be folded and kept in one's pocket. Flexible transistors may prove out to be cost effective as well because of the complex fabrication procedures of conventional semiconductors. Flexible transistors may turn out to be cost effective as well and may save billions of dollars of foundries and fabs in the modern world. Now we come to the fabrication of flexible transistors. Basically, organic thin film transistors or organic field effect transistors are the basic structures that can be used to build a flexible transistor. Carbon nanotubes and graphene, along with amorphous silicon and low temperature polysilicon semiconducting metal oxides, are the promising candidates for making flexible transistors, but the most commonly used materials are carbon nanotubes and graphene, which are used to fabricate flexible transistors. We would here discuss the fabrication of flexible organic transistors by using graphene and CNTs. Certain fabrication techniques are used for building flexible transistors by using carbon nanotubes and graphene. These techniques are further divided into solid, liquid, and gas phase fabrications that we would discuss in the next slide. So here we have the three phases for fabrication: solid, liquid, and gas phase. For solid phase fabrications, carbon nanotubes or graphene are supported on a solid and rigid wafer and are directly detached from the wafer, and they are then transferred onto a flexible substrate. That's how solid phase fabrication takes place. For liquid phase fabrications, carbon nanotubes or graphene are dispersed in a solution and is deposited on a flexible substrate by liquid phase approaches, including spin coating, inkjet printing, and nano imprint. For a gas phase fabrication, a CNT thin film is formed in a gas phase environment and directly dry transferred to a substrate to make flexible devices. But at present, there are no such techniques reported for graphene as far as the gas phase fabrication is concerned. So here we have the flowchart for the fabrication of flexible transistors. As you can see that nanotubes and graphene are the basic synthesis materials for the fabrication of flexible transistors, and on this flowchart you also see that we have solid, liquid, and gas phases separately defined, so that after the synthesis of nanotubes and graphene we have different ways of printing the films, the nanotube or graphene films, onto the substrate. So the solid, liquid, and gas phases are basically the differences in the printing of the film, in the transfer of the film from the rigid substrate to the flexible substrate. So as you can see, for nanotubes we have fixed catalyst chemical vapor deposition, and then it is directly transferred onto the flexible substrate. As far as solid phase fabrication is concerned, for graphene solid phase fabrication we have this molecular assembly, CVD, mechanical exfoliation, and then these synthesis materials, they make a film, then the film is transferred onto the wafer, and after that wet etching, R to R transfer, and bubbling transfer for the graphene takes place, so that we can transfer this film on the flexible substrate. As far as liquid phase fabrication is concerned, from nanotubes and graphene, for nanotubes we have this nanotube solution which is made of arc discharge laser ablation, and for graphene solution we have liquid phase exfoliation and RGO. These are basically synthesis materials for the solution, nanotube solutions and graphene solutions, and they are after that, when we have the solutions for liquid phase fabrication, these solutions are printed onto the flexible substrate by inkjet printing, sorting R to R or nano imprint. These are the steps that we take for the synthesis for the fabrication of in liquid phase for nanotubes and graphene. For the gas phase fabrication, we have this floating catalyst chemical vapor deposition, which we do for nanotubes, and then this film is transferred onto a freestanding film, and then that freestanding film, on certain environmental conditions for the gas phase, we dry transfer it onto the flexible substrate. So up till now we do not have any method for the graphene's gas phase fabrication. So up till now researchers are working upon it, but they do not have any method up till now. They haven't come across any method up till now. So this flowchart will, if you read it and if you carefully look at it, you will know how flexible transistors are fabricated by nanotubes and graphene. So after the fabrication steps, we come across the problem of performance enhancement of these thin film transistors. Basically, the key performance issues for thin film transistors are large carrier mobilities and high on-off ratios for high-speed operation and low energy consumptions. These are the tasks, these are the major things that we need to achieve in order if we want to increase the performance and enhance the performance of a flexible thin film transistors. In order to cater for these issues, we apply a technique of self-assembled monolayers. Basically, self-assembled monolayers of organic molecules are the molecular assemblies formed spontaneously on their surfaces by adsorption, and are organized into large ordered domains. So basically what it does is it assembles the monolayers of the organic molecules so that they can conduct well in different conditions. So basically here we have electrode surface modification with the self-assembled monolayers. This is basically the electrode surface of the flexible transistors, and for organic transistors to function well, charge injection from the electrode needs to be efficient. This requires the work function of the electrode to match well with the energy level of the organic semiconductor, such that the energy barrier for the charge injection is low, so that we can transport a charge within the semiconductor and the organic transistors at a high pace. For organic transistors, typical high work function electrodes such as aurum or palladium or indium tin oxide have been used for p-channel organic semiconductors, in which holes are injected and transported through the organic material, and this injection has been found that it has been found that the electrosurface modification with a self-assembled monolayer can be used to improve the charge injection into the organic uh, semiconductors. So this surface modification with self-assembled monolayers does prove out to be a solution for high if we want to achieve high carrier mobilities and high on-off ratios for these flexible transistors. We need to apply this technique of self-assembled monolayers, in which we can use aurum, palladium, or indium tin oxide for better performance of the flexible transistors. After the electrode surface modification, we can also enhance the performance of flexible transistors or thin film transistors by using dielectric surface modifications with self-assembled monolayers. Basically, the surface treatment of dielectric layer is an important way to improve organic transistor performance, since most of the charge carriers induced in the semiconductors are basically confined into first few nanometers of organic semiconductors from the semiconductor dielectric interface. So the dielectric surface chemical and physical characteristics thus play a very important role in the charge carrier transport. Additionally, dielectric surface treatment with self-assembled monolayers also affect the nucleation and growth of organic semiconductors. For example, a pentacene is an organic semiconductor having self-assembled monolayer, and it has the highest reported thin film charge carrier mobility. Its charge carrier mobility changes significantly depending on the types of hydrophobic self-assembled monolayer surface treatments. So dielectric surface modification also plays a very important role in the performance enhancement of the flexible transistors. So here we have a graph of the dielectric surface modification with the self-assembled monolayers. In these are basically transfer characteristics of fabricated thin film transistors. The black line in this graph represents the transfer curve for the device without the self-assembled monolayer treatment, and the red lines, as you can see, with self-assembled monolayers are represented here. So you can see that the transfer characteristics and the drain to source current for the treated dielectric surfaces reaches a higher value than the untreated dielectric surfaces of semiconductors. Below you can see the diagrams, the pictures for the these are basically the microscope images of channel region of fabricated thin film transistors. On the B picture is for the untreated thin film transistors, and the C picture is for the treated electrodes, and you can see the difference in both the images. After the surface modifications with self-assembled monolayers, we have the layer modifications, and we take self-assembled monolayers as the active dielectric or semiconductor layers for the organic transistors. The dielectric layer for organic transistors should be as thin as possible, and ideally with a high dielectric constant for low voltage operation. A well-ordered, densely packed self-assembled monolayer may be the thinnest possible high-quality dielectric layer that can be used in the semiconductors. We use self-assembled monolayers as a dielectric layer in the organic transistors for low voltage operations. As far as the semiconductor layer is concerned, to facilitate the charge transport, the organic semiconductor layer usually comprises of a pi conjugated oligomers and polymers. This requires the semiconductor molecules to self assemble into desirable orientation upon their vapor or solution deposition. These well-ordered molecular layers can be formed by a proper molecular design of chemical structures that favor crystallization in large order domains, or we can use self-assembly into mono and multi-layers. Using self-assembled multi and mono layers, we can we as a semiconductor layer we can improve the charge transport of the organic transistors. Now we take the case of self-assembled monolayers for patterning. Basically, for organic transistors, the active semiconductor layer has to be patterned in order to minimize the crosstalk between the devices. Additionally, both the drain and source electrodes need to be patterned so that they are separated by at most a few micrometers, not more than that, depending on application requirements. In addition to various printing methods such as inkjet printing, screen printing, and offset printing, self-assembled monolayer modified surface have been used for selective deposition of organic semiconductors through pattern wettability or templated growth. After having been discussed the fabrication and performance enhancement techniques for the flexible transistors, we come to the applications in real world, and this part will excite you most because of the fact that you're more known to these technologies, and the flexible transistor and the flexibility in modern electronics excites one and all. So first thing that I would be discussing in the applications would be flexible flat panel displays. As we all know that smartphone, mobile phone, and television and electronics companies look for innovation all the time. So a flexible display basically would provide the perfect uh, attraction to the users these days. And in recent years, there has been a growing interest from numerous consumer electronics manufacturers to apply this flexible display technology in mobile phones and other consumer electronic devices. So these flexible displays are basically a result of the flexible electronics and the flexible these flexible displays are basically made on flexible substrates using flexible transistor technology. Lately, Nokia has introduced the kinetic concept phone. This flexible OLED display allows the user to interact with the phone by twisting, bending, squeezing on however you like it, and folding it in different manners across both vertical and horizontal planes. So Nokia has already introduced it lately. As far as the TV screens are concerned, LG Electronics and Samsung Electronics both introduced curved OLED televisions with a curved display basically. Both companies recognized their respective curved OLEDs prototype television as first of a kind. So you see always companies uh, want to take the lead from each other. That's the case as well here. So flexible television screens are also have also been introduced, and uh, uh, this is one of its kind technology, and definitely this will become more common as it becomes user friendly and a little more inexpensive. Another very important application for flexible transistors is artificial skin. Uh, it is now widely accepted that skin sensitivity will be very important for future robots used by humans in daily life for different purposes. But despite this fact, relatively little progress has been made in the field of pressure recognition compared to the areas of sight and voice recognition, mainly because good artificial electronic skin with large area and mechanical flexibility is not yet available. Um, the fabrication of a sensitive skin consisting of pressure sensors would definitely require a flexible switching matrix that cannot be realized with present silicon based electronics. But organic field effect transistors and thin film transistors can substitute for such conventional electronics because organic circuits are inherently flexible, and flexible transistors are potentially ultra low in cost even for large area. Thus, the integration of organic transistors and rubber pressure sensors, both of which can be produced by low cost processing methods, will provide an ideal solution to realize a practical artificial skill whose feasibility has been demonstrated by researchers, and they have found it to be electrically functional even when these transistors are wrapped around a cylindrical bar and folded and bent. So this application will also prove out as a landmark in the applications of flexible transistors. So at last we are on the conclusion slide, and I would like to conclude this presentation by summarizing some key concepts and some key concept that we have discussed throughout this presentation. Initially, we started with the introduction of the flexible transistors, how flexible transistors are being researched upon. After that, we discussed the fabrication aspects and how can we fabricate these flexible transistors from organic field effect transistors, and we looked upon different phases of the fabrication of flexible transistors. After that, we discussed some performance enhancement techniques for flexible transistors. We looked upon the idea of self-assembled monolayers for better performance of flexible transistors, and how can we achieve good charge mobility in them. We discussed that as well, and after that we just yeah, discussed the practical applications and how flexibility in transistors is changing modern day electronics. So this was my presentation. I hope you guys enjoyed it. I want to thank you all for taking time out and listening to my presentation. Thanks a lot, and I would like to thank Professor Headley for giving me this opportunity uh, for to present this presentation in front of you guys. So I would like to thank you all.